Good morning, my students. Let's continue our time series model, okay? I like sort of review what we have learned last week, okay? Last week, we introduced two types of time series model. One is called distributed lag models. So it's like the equation 12.2. Okay, look at this PowerPoint. You can see 12.2. Is this one? Okay. In fact, this distributed lag model is the one with independent variables, including the lag of independent variables. So the general form can be expressed like 12.2. Okay, so this is the distributed lag model. What's the problem with the distributed lag model? The major problems: multicollinearity. Okay, and remember this one. This arrow terms is white noise. All right. Okay. Then the second model is what we call dynamic model. So dynamic model is the one with a lag of dependent variable as an independent variable. Okay? And what's the problem with dynamic models? So like 12.3. So we have the lag 1 of dependent variable y. And what's the problem with dynamic models? Huh? Multicollinearity? Well, if we express dynamic model as a distributed lag model, then multicollinearity problem does exist. But if I don't express as a distributed lag model and just using the dynamic model, what's the problem? Zero correlations. So the UT here has zero correlation problems. So we can do the we can check with whether this UT has zero correlation by using LM test. Remember that? Okay. This is what we learned last week. Okay. Now I'm going to continue what we have learned here. Especially, let me go back to our, since the dynamic model can be also expressed as a distributed lag model, let me go back to the distributed lag model. And talking about the other issue is granular causality. Okay, this is the section 12.4. Okay, and why do we, thinking about this one? Let's see the equation 12.2. Okay, this equation is used. Okay, let me ask you questions. When we do the regression analysis, all this is called regression analysis, right? Either cross-sectional data or time series data. We say this is regression analysis. Okay, and the regression analysis with this kind of expression, I mean distributed lag model, do we really thinking about the causality effect by using regression analysis? Do you mean the causality effects in business area? Okay, I'm not sure about engineering, but in business area, when we do the regression analysis, we say X variables are, by theory, as an important factors to affect the variation of the Y. But we didn't say X is the cause to lead to X, Y have some variations. We didn't say that. So there is nothing to do with the causality effect by regression analysis. Remember that? Well, remember that? This is the very basic concept in regression analysis. Unless the theory really insists the causality effects. Otherwise, in general regression analysis, we didn't really say X is the cause to effect Y variation. Remember that, okay? But here we wanted to say the causality, but we put another terms, say Granger causality. And this Granger is really an econometrician, famous econometrician. And he said that. So let me go to the PowerPoint of the causality. Okay. So what do we mean by Granger causality? It is say that it's a circumstances in which one time series variable consistently and predictably changes before another variable. So if we can make sure one of the variables will always precede the other variable happen, means this is Granger causality effect. Okay, especially for time series data. We do have something happen before, then something happen after, right? Because we have some lags. All this data with different lag means a lot, right? For cross-sectional data, the order of the observation doesn't mean anything. But the time series model, it does, and very important. You cannot change the order of the observation. Therefore, we can be sure that if we can have the evidence to show that one of the variable is always happen before the other variables, then we can say something, factor A, okay, always precede the factor B, okay? Then we can say A Granger causality cause B. Okay, then how do we check? How do we check whether we have this situation or evidence? Okay, so look at this equation. I wanted to show two equations. Actually, it's 12.20 and, well, there's no the other one. Oh, then let me show my let me show my okay, let me show. I wanted to show this too. Okay, look at this one. This actually, the first one, 12.20, is the same as our textbook. Okay, and 12.21. Oh, it must be also in our textbook, but there's no in the PowerPoint. Okay, so let's see this one. Look at 12.20 using y as a dependent variables, and the lag of the y plus the lag of a variable a as independent variable. And the second one is using a, okay, as a dependent variable, then the lag of a as well as the lag of y as independent variable. All right? Okay? So actually is using, they all have the same independent variable but different dependent variable. One is using y as a dependent variable, the other one is using a as a dependent variable. Okay, let's see this one. Continue. How to do the continue? Okay, look at this one. Maybe it's better to use in mine. Look at this one. Look at this one. Now hypothesis all lambda 1 up to alpha 1 up to alpha p. Look at the alpha. Look at this one. When I say alpha, means this now this hypothesis testing apply for these two equations. Where's the alpha here? Oh, the alpha. Okay. So if I put A as one of the variable and using Y as a dependent variable, or if I use A as a dependent variable, those alpha is the leg of Y, the coefficient of leg of Y variable. You see that? So if I can test all the alpha 1 is significant, so all the alpha from alpha 1 to alpha p for equation 12.20 means those A is significant to affect the Y. If the alpha here means Y is significant to affect the A, right? Okay, but there are several situations. We may have 4 situations. One is the alpha in 12.20 significant, and 12.21 is not significant, or even reverse, not significant 12.20 and significant 12.21. So there's 2 cases, right? The other one is both of them are not significant, and this is the third one. The fourth one will be all significant, right? Right? So look at this one. Let me see. So if we jointly test alpha 1 and alternative hypothesis, at least one alpha j is not significant, it's not equal to 0. Okay? So there are 4 cases. The first one is what we call unidirectional causality from A to Y. What does that mean? Means all the estimated alpha in equation 20 is significant, different from 0 as a group, but not for the set of estimated alpha j coefficient in the equation 21. Okay, so means that this alpha significant, but this is not significant. So we say A grandeur cos Y. Can we say A grandeur cos Y? Let's see. And there's a 2 unidirectional causalities, means if Y to the A, so means equation 12.21, all the alpha are significant. So we say Y grandeur causes A, right? Okay. Then the third one is bilateral causality. So means both A and Y are significant, different from 0 in both regressions. Then independence means none of them significant. Okay, so what is the grandeur causality means? About these 4 cases, the first one, second one, and the third one is either one of them can be the grandeur causality for the other variables. Okay, there's among these 3 cases, 2 can be identified as the grandeur causality. Okay, but you have to know which one precede which one. Okay, and remember, if we implement this Granger test, we need to consider several variables. So you cannot just go to the test to do the hypothesis test for the regression 12.20 and 21. There are some considerations we need to know before we do the Granger causality test. Okay? Remember, we have some lags, right? So if we do this Granger causality, the test, the number of lags terms is very important. So the P lag, how many lags do you have to use? Okay, maybe you need to have some theory as a foundation, as a base to support the lags the lag of terms you choose. Okay, all right. And of course, how do we choose that number of lags? We can use like archaic, Schwartz, or similar criterion. Okay, we will talk about that later on. Okay, all right. And this is the first one. You have to know that. Second one, we have to assume that error terms enter Granger test are uncorrelated. Means, since that is what we call distributed lag model. Actually, distributed lag model, we need to make sure the error terms is white noise. Okay, so this is the second factor you have a consideration. Okay, the third one, okay, is important. Okay, we say that you have to check or guard against spurious causality. What do we mean by spurious causality? When we say A causes B or vice versa, it is quite possible that there's a lurking variable. What do we mean by lurking variable? A, if we say A causes B, there are something variables is C, which the variation of A can be changed by C, and B also can change by C. So if we say A causes B, it is really not A and B itself, but the lurking variable C. Means something hide behind A and B. Okay? All right? So this is spurious. This is what we call spurious causality. Okay? All right. Then the fourth one we need to know is, and this is also important, the critical assumption underlying the Granger causality test is that variable under the study, such A and B, are stationary. I think this is the main topic we want to discuss today. Okay? Time series data usually is non-stationary. But in regression analysis, since it is regression analysis, we need to assume all the variables are stationary. Okay? So this is the main topic I'm going to talk about later on. So this is the consideration. We need to know that if you do the Granger causality test, make sure all the variables are stationary. Okay? All right? Huh? Number 3, which one? Well, usually, okay? For example, nowadays the inflation is high, right? So if A variable is also caused by inflation and B is caused by inflation, but we see the relationship of A and B, they all caused by inflation. Inflation, especially for time series data, right? Those are, then inflation will be the lurking variables.
So we just do more research.
Yeah. Yes. And usually, if you use the variables, which use nominal data, not nominal, means like interest rate or something, which is using, then factor out the times. You know, in business, we usually do this one, right? We have to, like, for example, if I'm using the data nowadays, okay, I need to adjust my inflation rate. So I will change my nominal scale, not nominal scale, nominal into what? Into, have you heard about real interest rate and nominal interest rate? Nominal interest rate is the one included inflation, but real interest rate is the one, you know, really eliminate the inflation rate, okay, factors. So if we use all this different time series data, but we adjust to the same years, dollars, then there's no lurking variable about the inflation. That's why this is what we are saying. One of the examples say lurking variable. Okay? All right. Then number 5. Okay. Number 5 say that there's another situation called co-integrated. Co-integrated. Okay, we'll talk about this one too. Okay, let me just say a little bit about co-integrated. Means that many times, or in some situations, maybe X and Y are non-stationary. Okay, but together they can be, we can test whether it is co-integrated. If after we test those co-integrated situations, no matter individual X or Y are stationary, but combine them together, if we can check whether they are co-integrated, then that's safe. We also can do the granular causality. This is what we mean. Understand it? So we'll talk about co-integrated, the concept of, or the concept of co-integration, and also the concept of stationarity. Okay, this is the main topic. Okay, all right. Let's see. There's some examples. Okay, if I wanted to see this consumption and income. Okay, look at this one, A and B. Okay, this is one of the Y variable. This is one of the X variables. Okay, I'm using look at this one. Okay, so this one is using the lag of itself and also the PDI, and using PDI as a Y and the PDI itself and the PCE. PCE means personal consumption expenditures. PDI means personal disposal income. Okay? All right? So this is granular causality test. We can do this granular causality test. Okay? And, okay, so I'm doing this one. And since this, I'm using alpha, beta, gamma, delta. So I'm checking with the alpha, beta, and the delta. So I'm checking this variable and this variable. Do you know what is this? This is the T. T means time. Okay? Usually, for economic data, time is the lurking variable. Therefore, many times we put the T to eliminate the lurking variable of inflation. Okay, this is for economic data. I don't know about your Yes. Usually, this T can be considered as one of the inflation, because from the time, you know, all these T's means 1, 2, 3, 4, 5, 6. So if the number of the bigger means the time is later, and if we do this one, then we eliminate the inflations usually. Not T, just T. Lambda is coefficient. Lambda is coefficient, and T is the variable. You know, you can see a lot from time series models. Okay? All right. Then the Granger causality examples. Okay. Since we don't have that examples in the book, just say some words on it, no examples. So I show one of the examples here. Okay? Then I'm checking with this beta, all the betas and all the delta. And I do have 4 situations, right? Then that's it. So I can use, okay, let me say something about this one, okay? I like to, if it is possible, I also like to cover all these models. Well, let's see. This is continue my co-integration concept, okay? However, while individual non-stationary is possible that the variable in question are co-integrated. In that situation, as in the case of univariate non-stationary variable, we will have to use error correction mechanism. There's another model, say error correction mechanism. Then it is another model is ECM. Okay, if we have time, I like to cover that too. If I don't have, I have to cover the major one. Then do the rest of them. Okay, I'll see whether we have time. Okay, and by the way, the Granger, the most application of the Granger causality is to forecasting. Okay, before you do the forecasting, you need to know some variables are really the some events happen before the one you want to forecast. So Granger causality test is important for forecasting. Okay, all right, and let's see, what else? Okay, this is one. I'm running the. This I think I just use what? Oh, this is the OLS. Okay, I think this one. Oh, well, that's it. Okay, all right. All the Granger causality. Any questions about Granger causalities? I wanted to mention this one is I want to bring out the concept of stationarity and also co-integration, as well as the forecasting purpose for Granger causality test is important. Okay, before you do the forecasting. Any questions? Okay, if you don't have any questions, then let's go on to let's see, what is it? This one. Okay, let's go on to our very heavy topic of chapter 12.5, spurious correlation and non-stationarity. Okay, what do we mean by spurious? What do we mean by spurious correlations? What's the meaning of spurious? What's the meaning? The words in this English words. suddenly happens. Anything else? Spurious usually suddenly happen. There's something unreal, fake. Huh? It's fake, right? Okay? So spurious means, just inflated. It's fake. Okay? So spurious correlation is a strong relationship between two or more variables that is not caused by a real underlying causal relationship. So it's like if we have this lurking variables, actually we see A and B are highly correlated, but in fact, they are not highly correlated. If I take out the factor of C, embedded in the variable, then they have no relationship at all. And actually, without taking out the variable C, we really see the highly correlation between two variables. Or here we also can say more variables. Okay? So it's a fake. It's a fake. Okay? And a regression in which dependent variables and one or more of independent variables are spurious correlate is called spurious regression. And the t-scores and overall fit are likely to be overstated and untrusted since it is spurious. So when we see all the t-scores is big and those p-variables is small, right? And overall test, f-test, is also significant, right? But everything is overstated and also untrusted, okay? And one cause of spurious correlation is non-stationarity. Okay, then we have to learn what is stationarity and non-stationarity, okay? All right? Look at the definition of stationarity, okay? A time series variable xt is stationary if the mean of the xt is constant over time. The variance of xt is constant over time. And the simple correlation coefficient between xt and t minus k. So k can be any lag. Depends on the length of the leg, but on no other variable. So these three conditions are important and have to all satisfied. This is what we call stationary. Mean constant, variance constant, and the simple correlation coefficient between xt and xt minus k. It only depends on the length of the leg. Okay? If one or more of these properties is not met, then xt is non-stationary. Okay? And this problem is known as non-stationarity. In other words, for time series analysis, we need all the variables is stationary. Okay? So all the variables satisfies these three conditions. It is hard, right? Okay, then continue. Some variables are non-stationary because they rapidly increase over time. Adding a time trend, okay, Steve, this is what we say. Adding a time trend to the regression model can help avoid spurious regression in this case. That's why we put t as an independent variable, okay? Unfortunately, for many variables, this does not elevate non-stationarity. If they are not just because of the time, okay, they do have some other reasons to be non-stationary. Then using t doesn't work either. Okay, all right? So non-stationarity often takes the form of random walk. Okay, so let's explain what is the random walk. So there's a lot of terms like this one. Have you learned it before already? Yeah, okay, I think all these terms is important before we understand this issues, okay? A random walk is a time series variable in which the next period's value equals the year's value plus a stochastic error terms. Means equation 12.20. So it means there's a relationship of the gamma with the previous y t minus 1, and v is, what do you mean? Classical error terms. So white noise. It's really random, okay? So it means that the current yt just affect the previous yt minus 1 with the coefficient of gamma, okay? And if gamma, look at this one, if gamma absolute, gamma less than 1, then yt is called stationary. What do we mean by gamma equal to, what does that mean? For engineering, there's no problem. I don't have any problem, but for business students, I need to explain. This one means what? Means negative gamma, this one. So what does that mean? If I say yt gamma yt minus 1 plus, this is vt, okay, and this is just random walk. What does that mean? If it is between negative 1 and positive 1, whatever happened, if it is, since 0 is in between, right? So if it is positive, means the current terms will be affected by the previous. So for example, if this is 0.5, so means that this is the current numbers, and but this is the leg one, and this current yt will be affected by yt is equal to yt minus 1, just times half. So if I say then yt minus 1, yt minus 2. Okay? So the effect to the previous leg, the longer, the smaller. Okay? And this is the positive relationship. Also, as well as the negative. If I put the negative term, it's also the same. Positive will be something like this one, but getting smoother. And the negative will be like this one. Okay? It's a zigzag. But the effect is getting smaller and smaller. So this is what we call stationary. That means it can be controlled. The future values of y can be controlled by, the previous one. Okay? As long as the time is getting extended to longer, the effect is getting smaller and smaller. So it can be controlled finally up to 0. This is what we say stationary. If our math is not that good, but thinking about this, the implication or the idea of these math expressions, I think we all understand that, right? This is called intuition. Not math oriented, but intuition. So of course, if less than 1 is stationary, then greater than 1 will be non-stationary. So if looking at this one, if this is greater than 1, what does that mean? means everything is outflowed, right? It's outflowed. Nothing can control. You cannot control it, right? It's greater than 1. It can be a lot and just blew everything, either positive or negative. So means you cannot control. It's just it's not converge. It's what? Diverge. Okay? So this is what we call non-stationary. Well, exactly if it is equal to 1, means 2 cases, positive 1 or negative 1. Okay? And this is what we call unit roots. So there's a terms, unit roots. Okay, remember that. Alpha, gamma equal to 1, absolute value of 1 usually is positive 1. Okay? It can be negative 1, but most of the situation is positive 1. Okay? This is called unit roots. Okay? Unit roots, what does that mean? The current value is the same as the previous one. Okay? All right? Let's see. So there's an example. Look at example. Y variable is the price, and the X variable is tuition. So price in dollars of a gallon. What's that? Is the is the price is this is the price of gasoline. Okay, so price is the price of a gallon of gas in somewhere Portland in the United States. It's in Oregon. Okay, then tuition is a tuition in dollars for a semester of study at some colleges in Los Angeles. So this is all in California, state of California. Oh no, this is California, but this is the state of Oregon. Okay? Does that make sense? You do this regression. The price is a gasoline and the tuition. But look at these numbers, is significant, right? This is what we are saying, that this is just spurious. Nonsense. Yeah, spurious we also can express as a nonsense. Right? Okay? To ensure the equations are not spurious, test for non-stationarity. Okay? First of all, visually examine the data of a diagram of data. Second, standard methods of the testing for non-stationarity is what we say Dickey-Fuller test. Or later on, you are going to see augmented Dickey-Fuller test. They're pretty similar. Okay, usually we use augmented Dickey-Fuller test. Okay, then let's introduce the Dickey-Fuller test. Later on, I'm going to use in the examples. Okay, now I have do some those introductions by words, but later on I'm going to use examples. So later on, let's do together, okay? The Dickey-Fuller test examines the null hypothesis that the variable in question has a unit roots. Remember, what's the unit roots? What's the unit roots? Unit roots is want to check the gamma, whether it is equal to 1. Okay? So let's see. So let's see this one. To understand the Dickey-Fuller, started with this. This is the same equation, 12.22. And if gamma less than 1, then y was stationary. So now let's look at equation 12.26. This means that either left-hand side and right-hand side of the equation 12.22 is minus the previous periods. Okay, so it becomes like this. Any questions about this one? for business students. You don't have any problems with this. Is there any questions about this? No, right? Just using 12.22 and minus yt minus 1 and also yt minus 1, both sides. Therefore, this one become as the term, and this one, since before we have gamma, then minus 1. So like this one. So we will express 12.22 to 12.26. So usually what do we express this one? Previous minus the current period minus the previous. So usually we're using delta. Delta means change. Change. So look at this. If we define, okay, you need to know how do we define. And this is the custom, also the habit. We always do that. So you need to know the delta yt is really using t minus 1. But do not do the reverse. Okay? Do not do the reverse. It's using yt minus 1. Okay? Look back to 12.26 and this one. This is delta yt. And this one, they express as beta. So look at this one. Did you see? Beta equal to gamma minus 1. Understand it? Understand it? You all follow me? Okay. Okay. So I can express 12.26 into 27. So if I do the null hypothesis of beta equal to 0 means what? If beta 1 equal to 0 means what? Gamma equal to 1, right? And what does the gamma equal to 1 means? Random walk, right? And we're checking less than 0. If beta 1 less than 0, what does that mean? Is less than 0 means what? The absolute value is within 1, which is stationary. Okay? So if we reject the null hypothesis, it means what? This is called non-stationary, right? This is called stationary, right? This one is stationary. This is non-stationary, right? So we wanted to reject the null hypothesis in order to make sure, infer that we do have stationary variables. Does that make sense? Is it okay, Steve? Huh? Huh? Excuse me? You mean beta 1 less than can be non-stationary. Why? Huh? Gamma equal to -2. Well, let's take a break. Okay. Let's take a break. Let me thinking about it. What you say?